Let's take a look at then, continuing our conversation here, conservation of mechanical energy, looking at a problem-solving strategy. So for conservation of energy, take the following steps in applying the principle of conservation of energy. Define your system, which may consist of more than one object. Okay, so you're going to take a look at it. Do you have, several things going here? Do you got a box on a surface, a pulley, and a sphere being dropped? Look at how you're going to take it apart, just like you did with forces, and then try to determine which of these are potential energy versus kinetic energy. Select a reference position for the 0 point for gravitational potential energy, because this could be that point where you have your starting point and everything goes to 0 like we've seen before. Determine whether or not non-conservative forces are present. Most of the time in problems, it will clearly state disregard friction or disregard air, the resistance due to air. Okay, so look for those clues. And then if mechanical energy is conserved, that is, if only conservative forces are present, you can write the total initial energy at some point as the sum of the kinetic and potential energies at that point. Then write an expression for the total final energy, kinetic energy final plus potential energy final. At the final point of interest, because mechanical energy is conserved, you can equate the two total energies and solve for the unknown. So let's look at one here. One that's that we're gonna break it apart in pieces. It may look like it's complex, but when we take it apart, you'll see that we can really kind of do a stop action on this. So we've got a diver, 755 Newton diver, drops from a board 10 meters above the water surface. They want us to use conservation of mechanical energy to find his speed 5 meters above the surface of the water. So it's kind of like running a newsreel and stopping it. And you're going to see, as you do this, you got to think in your mind, I'm going to stop it just as he reaches 5 meters above the water. And that's where the problem stops. If we're going to continue the path, we'll pick it up from there. So we start looking at defining all of our givens. So we've got the force of the driver, mg, is equal to 755 newtons. The initial value is given as 10 meters, and the final value of the problem would be 0 meters. Okay, but we're going to stop him at we're going to stop his speed 5 meters above the water surface. So we need to look at those. So we're going to use conservation of mechanical energy to find his speed 5 meters above the water surface. So we start with our equation. You might as well start with this one because, rather than starting with potential energy, kinetic energy, blah, 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 let's just start with the grassroots equation here. 1/2 mv squared initial plus mg y initial. That's the beginning side of the problem. The ending side of the problem, 1/2 mv final squared plus mg y final. So put in every value that you can and every 0 that you can. Okay, so we've got 1/2 the mass times the velocity initial squared. Well, he starts off at 0, so that whole term goes away. Then we have his potential energy, 755 newtons times 10 meters above the water. So we've got everything we need there to determine his potential energy initial. Then we set that equal to 1/2 mv final squared. So 755 newtons divided by the gravity, okay, 9.8 meters per second, okay. And then we can see we've factored out the v final squared because we don't know that velocity. And then we add to it the potential energy, 755 newtons times 5 meters. That's where we're going to stop him mid-flight. So when we solve all of this, all we have left on the left side is 7,550 joules is equal to 38.5 kilograms times the velocity final squared plus 3,775 joules, the potential energy at 5 meters. So now let's pull out the one unknown that we have here. So what we're going to do is we're going to move the 7550 to the other side of the relationship. We're going to subtract it one from the other. So we're going to subtract 3775 from 7550 because that makes sense in the lineup here. And that becomes our numerator. The denominator then becomes 38.5 kilograms. And we're going to solve for the final velocity at that point. And when we do that, you're going to look at this and you go, how do I get joules and kilograms? Okay, this is where I told you're going to have to remember how to decompose joules back into Newton meters, back into kilogram meters squared per second squared. So when you decompose joules back to kilogram meters squared per second squared, what's going to happen is everything is going to drop out, that is mass-wise. So all the kilograms are going to disappear, and we're going to be left with 98 meters per second squared, meters squared second squared. Notice it's meters squared second squared. Why? Because I've got a square on the other side, on the left side. When I take the square root of both sides of these, that square is going to disappear. The square root then is going to resolve this to 9.9 meters per second. So when we take this snapshot in time with this guy dropping through space 5 meters above the water, he's moving at 9.9 meters per second. So the next part of the problem says, find the speed of the diver just before he hits the water. So now we're going to move him all the way down here just before he hits the water. So we set up the relationship the exact same way. Put in the values that we know. This time we're going to solve for him traveling, in essence, the entire distance. Okay? So when we do that, 755 newtons times 10 meters gives us 7550 joules, and on this side of the equation, when I divide through by the acceleration into the newtons, again, you're going to have to decompose that. Newtons is kilogram meters per second squared. You're going to end up with 38.5 kilograms. We're going to factor the velocity final squared to the other side of the relationship, divide through by 38.5, and I get 196 meters squared second squared. I take the square root of both sides. I get 14 meters per second squared. So just before this guy comes splashing through the water, we take a snapshot, and he's moving at now 14 meters per second. Okay, so now they're saying if the diver pushes off so that he leaves the board with an initial speed of 2 meters per second. Remember in the last problem, he just dropped off. He started at 0 and he just dropped off. Now we're going to have him jump off. So he's going to have an initial speed of 2 meters per second. We want to find his speed when he hits the water, use conservation of energy. Okay, so no losses. So again, we run through the same thing, but now our initial velocity is not 0, it's 2 meters per second. Set up the problem the same way. Put in your values, 77 kilograms, 2 meters per second squared. Okay, so that's our relationship on the left side. Since we're not starting with 0, we have the same 755 as our newtons, 10 meters, and again 77 kilograms, because that was our guy. That was his mass. So now when we run this through, again, just like we did before, we get down here to the bottom, 200 meters squared per second squared, take the square root of both sides, and now I have him moving at 14.2 meters per second. Not a lot, just a little bit more, but there was a little bit of speed added to him falling, of being accelerated down rather than just falling. So when we come back, we'll look at another example.